After studying this module, you shall be able to know the color of various coordination complexes, as well as you will learn the reason behind the color in these complexes. You can identify various laws governing the absorption of radiation in the complexes. Also, you can evaluate electronic spectra of these complexes. Introduction. A large number of coordination complexes are colored, whereas most of the organic compounds are colorless. But there are certain organic moieties which are very intensely colored due to extended conjugation in these systems, such as beta-carotene, which is a terpenoid derived from isoprene units. Some of the extremely important properties of complexes are related to their specific electronic configuration. For example, blood is red due to heme group, which is a coordination complex of iron. Plant leaves are green due to the presence of the pigment chlorophyll, which is again a coordination complex of magnesium. Both heme and chlorophyll are porphyrin based systems with metal at the center of the porphyrin ring. The absorption spectrum of these species is represented in figure 1. The various other examples include copper sulfate pentahydrate, a complex of copper, blue in color, also Persian blue dye, which is a coordination complex of iron, etc. The color originated is actually due to electronic transitions occurring between the various energy levels, with the gap equivalent to the energy of the visible spectrum.
We will discuss color of the coordination complexes. First of all, we will look the origin of color in the complexes. Crystal field theory can elucidate the cause behind colors of the coordination complexes. Sometimes one or more electrons can possibly temporarily leap up from the d orbitals of lower energy to that of higher energy, which then actually generate a brief excited state atom. The energy of the photon taken in is the difference of energy between the excited and ground state, and is inversely related to the wavelength of the light. Only certain wavelengths represented by lambda of light are absorbed, and a compound appears of the color complementary to the absorbed wavelength. This is discussed in table. Different ligands create crystal fields of diverse strength, and thus dissimilar colors can be observed. For a given metal ion, a weak field ligand will generate a complex with a small delta value, and such a complex absorbs light of extended lambda or lower frequency. On the contrary, stronger ligand field generated due to strong field ligands will create a huge delta gap, thus will absorb light of shorter lambda and thus higher frequency. In order to comprise color in a substance, it must include an electronic transition with the energy change between 1.8 and 3.1 electron volt, which corresponds to the light in the visible region, that is approximately 400 to 700 nanometer. This has been represented in figure. This type of low energy transitions need intimately spaced energy levels, some with and others without electrons. Numerous dyes are bulky organic molecules with comprehensive pi bonding, which provide closely spaced occupied pi and unoccupied pi star orbitals. Most often, transition metal complexes are colored due to the reason that crystal field splitting provides closely spaced, partially filled electrons. Table corresponds to the visible light absorbed and the corresponding complementary colors are given. Consider the titanium octahedral complex, which absorbs in green and yellow part of the spectrum and appears violet, which is the resultant complementary color. This has been shown in figure, which represents the electromagnetic spectrum along with the color wheel and the absorption spectra of the titanium complex, where wavelength has been represented in nanometers and absorbance has been represented on the y-axis. Next, we are going to discuss Lambert's Beer law. There are two laws governing the absorption of radiation, which are related to the incident light taken as I0 should be equal to IA plus IT, where IA is the intensity of light absorbed, that is, the small a represents the word absorbed, and IT is the intensity of light transmitted, where the small t represents the word transmitted. Whole of this is represented in figure. The assumption that no reflection or scattering has taken place is also taken into account. The two laws are namely, first is the Beer's law and the second is the Lambert's law. Beer's law states that intensity of a beam of monochromatic light diminishes exponentially with an increase in the concentration of the absorbing species arithmetically. Therefore, dI by dC is directly proportional to the value of incident light, where C is the concentration. This means that the decrease in the strength of the incident light I with concentration C is proportional to the strength of the incident light I. Eliminating and initiating the constant of proportionality represented by K1, the equation transforms as minus dI by dC is equal to K1I. The terms are reshuffled and we get minus dI upon I is equal to K1 dC. On integration, the equation changes minus ln I should be equal to K1C plus B. The equation is named equation. B is the integration constant. Now, when the concentration becomes equal to 0, there is no absorbance. Thus, the condition becomes I is equal to I naught. Substituting the value of I in equation 1, it changes to minus ln I naught is equal to K1 multiplied with 0 plus B. It results in the value of B as minus ln I naught. This value can now be substituted in equation 1 and we get minus ln I is equal to K1C minus ln I naught. Ln I naught minus ln I will now be equal to K1C. Since log A minus log B is equal to log A by B, thus the equation now changes to ln I naught by I should be equal to K1C. Removing the natural logarithm, we get I naught by I should be equal to e raised to the power K1C. Taking inverse on both the side, it becomes I by I naught is equal to e raised to the power minus K1C. Now the equation reshuffles itself to give I is equal to I naught into e raised to the power minus K1C. The equation is named as equation represents the required equation of the Beer's law. On plotting absorption versus concentration, a straight line is obtained since absorption is negative log of transmittance. The graph of percentage transmittance versus concentration is an exponential decay. This has been represented in figure where absorption versus concentration graphs for the Beer's law has been shown. Lambert's law says that the pace of lowering in the intensity of monochromatic light with the width of the medium is directly proportional to the strength of incident light. This means minus di by dt is directly proportional to I, where t is the width of the medium. This suggests that decrease in intensity of the incident light I with thickness T is proportional to the intensity of incident light I. Eliminating and initiating the constant of proportionality K2, the equation can be written down as minus di by dt is equal to K2I. The terms are rearranged to give minus di by I is equal to K2 dt. On integrating the above equation, we get minus ln I is equal to K2t plus d. This is equation where d is the integration constant. Now, when concentration becomes equal to 0, there is no absorbance. Thus, I becomes I naught. Substituting the value of I in equation minus ln I naught is equal to K2 multiplied with 0 plus D. This gives us minus ln I naught equal to D. The value of D is now substituted in equation. This gives minus ln I is equal to K2T minus ln I naught. This rearranges to give ln I naught minus ln I is equal to K2T. Again, since log A minus B is equal to log A by B, the equation can be written down as ln I naught by I is equal to K2T. Removing the natural logarithm, we get I naught by I is equal to e raised to the power K2T. Making inverse on both the sides, we get I by I naught equal to e raised to the power minus K2T. This gives us I is equal to I naught into e raised to the power minus K2T. The equation is written down as equation which represents the required equation of the Lambert's law. On plotting absorption versus path length, a straight line is obtained. Since absorption is negative log of the transmittance, plot of transmittance versus path length is an exponential decay. This has been represented in figure. The graphs are very much similar to the one obtained from the Beer's law, as can be seen by comparing figure 4 and figure 5. Lambert-Beer's law can now be stated by combining the two equations, that is equation 2 and equation 4. The law states that the rate of decrease in the intensity of the incident light is directly proportional to the concentration and path length traveled by the incident light. This can be written down in the form of an equation where I is equal to I naught e raised to the power minus kct, where k is the multiplication of k1 and k2. Converting the natural logarithm to base 10 and capital K should be equal to k into 0.434. This gives I is equal to I naught into 10 raised to the power minus capital K C T. The terms are rearranged, giving I by I naught is equal to 10 raised to the power minus capital K C T. Taking inverse on both the sides, we get I naught by I is equal to 10 raised to the power capital K C T. The log is now taken on both the sides to give log of I naught by I is equal to capital K C T. This equation is now called equation. Since transmittance represented by capital T is equal to I by I naught and absorbance represented by capital A is log of 1 by T, thus absorbance A is equal to log I naught by I. This is named as equation. From equation 5 and 6, now it can be concluded that capital A absorbance is equal to capital K C into T. Instead of capital K, epsilon can also be used. Thus, A is equal to epsilon C T. This is the required Lambert's-Beer law. In this equation, capital A represents the absorbance, which can also be called optical density. Epsilon is the molecular extinction coefficient, or can be said as absorptivity. It is given the units centimeter square per mole. C represents the concentration of the given solution in the units of moles per liter. T is the path length, normally 10 millimeter or 1 centimeter. Absorbance is a dimensionless quantity. An absorbance of 1 corresponds to 90% absorption, and an absorbance value of 2 will correspond to 99% of the absorption. The spectra from spectrophotometers are mostly given in the format of absorbance versus wavelength, or the percentage transmittance versus wavelength. This has been represented in figures. The value of molar extinction coefficient is characteristic for species absorbing radiation. In spectrophotometers, the source of light is mostly the tungsten lamp that produces white, ultraviolet, and infrared radiations. Since the Lambert-Beer's law is applicable only to the monochromatic light, the monochromator, which serves as a diffraction grating, selects a very narrow band of light which passes through the sample that absorbs a certain fraction and transmits the rest. It is through a detector which further sends it to the computer programmed to convert it to some presentable signal, which is in the form of a graph. This has again been shown in figure demonstrates the working of spectrophotometers along with the displayed results in the form of a graph. Now we will discuss various deviations from the Beer's law. The Beer's law states that if absorbance, represented by capital A, is plotted against concentration, represented by small c, is a straight line, then passing through the origin, but many a times a deviation from a linear relationship, evidently shows the collapse of Beer's law. Beer's law is applicable for a huge range in terms of concentration, with the condition that the structure of the colored ion or non-electrolyte does not alter along with the concentration, even in their dissolved state. The presence of a foreign substance whose ions do not retort chemically with the colored components may affect the absorption of light and can in addition amend the value of extinction coefficient. There can be two types of deviations from the Beer's law. The first is the positive deviation, when a little modification in the concentration generates a massive change in the value of absorbance, then we get a positive deviation. Second one is the negative deviation, when a huge alteration in concentration creates a small change in the value of absorbance. This gives a negative deviation. We will discuss the cause of these deviations. The departure from the Lambert-Beer's law can be broken down to three types of classes according to their causes. First is the real deviations. They correspond to the fundamental deviations because of the restraints of law itself. Second is the chemical deviations, which are observed owing to a specific chemical variety of the sample which that is under analysis. Next is the instrumental deviations. These deviations occur due to the absorbance measurement methods adopted. All of these deviations will be discussed one by one. First of all, we will take real deviation. Lambert-Beer law is useful to describe the absorption tendencies of the solutions of relatively lower concentrations, specifically up to 10 raised to the power minus 3 molar. When concentration of the solute in solution is relatively higher, the solute starts to act differently owing to interactions by solvent and other nearby solute molecules. On many occasions, hydrogen bonding interactions are also present, which further enhance the deviations. Sometimes concentration of the solute is very high and they start screening neighboring molecules, thereby shadowing them from the incident light. Next, we will discuss chemical deviations. Chemical deviations occur due to the chemical phenomena that involves association and dissociation of the solute molecules. Also, interaction of the solute with solvent molecules produces a species with different absorption characteristics. For example, phenol red endures a resonance makeover when hailing to the basic variety, which is red in color, from acidic, which is yellow in color. Because of the resonance involved, the electronic allocation of the bonds within the molecule transforms along with the pH value of the solvent in which it is dissolved. This has been represented in figure, which specifically shows the change from yellow to red and vice versa. The absorption spectrum of the phenol red has also been demonstrated along with the various pH values. The next type of deviation is the instrumental deviation. Lambert-Beer's law is formally followed when a monochromatic radiation source exists. Mostly monochromatic source of radiation with continuous distribution of wavelengths is used along with a monochromator to create a monochromatic beam from this source by using diffraction grating. This can cause the deviation since completely monochromatic light is not produced by the monochromators. Further, if the stray or scattered radiation produced by scattering of light by the surfaces of lenses, mirrors, gratings, filters, and windows is absorbed by the solute, a deviation from Lambert-Beer's law is observed, similar to the deviation due to polychromatic radiation. In case cells holding blank as well as analyte solutions have unequal path length, it is definite to display a deviation in Lambert-Beer's law.
Summary. The electronic configuration of complexes gives them some important properties such as color that originates due to the electronic transitions occurring between the various energy levels with the gap equivalent to the energy of the visible spectrum observed. Only certain wavelengths, that is corresponding to lambda, of light are absorbed and the compounds appear of the color complementary to the absorbed one. There are two laws governing the absorption of radiation which are related to the fact that the light incident taken as I0 should be equal to IA plus IT, where IA is the intensity of light absorbed and IT is the intensity of light transmitted. The assumption that no reflection or scattering has taken place is also taken into account. Beer's law states that strength of the beam of monochromatic light diminishes exponentially with an increase in the concentration of the absorbing species arithmetically. Lambert's law states that strength of a beam of monochromatic light diminishes exponentially with an increase in the thickness of the absorbing medium.